In this video, we're going to look at another single bonded functional group, and this single bonded functional group gives rise to family of molecules known as ethers. And so what we're looking for here is, as it shows in this little schematic, some sort of carbon chain represented by R, single bonded to an oxygen, that is also then single bonded to another carbon chain. So in this case, oxygen becomes part of the chain. And that's new in terms of functional groups from what we've seen previously. So here you have an example, methoxyethane. So here's a carbon, so that would be an R group. Here's another carbon, and so within the chain we have this oxygen molecule or atom. So there we go, oxygen is part of the chain. So let's look at naming. There's two actual naming systems that I'd like you to be familiar with. Obviously the IUPAC system, and so we'll look at that first. So the IUPAC system deals with a branch and an alkane. So the alkane, not surprising, is going to be, you're going to look for the longest carbon chain that's attached to the oxygen. It always has to be attached to the oxygen. So that is an ethane, and so this other side of it, this other bit, is a branch, and that includes the oxygen. And so this particular branch is known as an alkoxy branch, and so I hope you can see why that's known as an alkoxy branch. It has the oxygen attached to it, and it has some sort of alkyl component, so in this case a methyl. And so that becomes, as an alkoxy branch, because it has one carbon, a methoxy branch. And so the name then becomes methoxyethane. So again, the methoxy component comes from this branch, and the ethane component is just the longer of the chains. In this case, there was two carbons attached to the oxygen, so that becomes the ethane component. So that's the IUPAC system, where you have an alkane attached to an alkoxy branch, and the alkoxy branch becomes a prefix. The second way then is a common name, and a common name simply takes all the branches. So that's a methyl branch, and that's an ethyl branch, and adds the name ether because that is an ether functional group. So the name is a little simpler. When you put it together alphabetically. So ethyl comes first, methyl comes second, and then you have ether. So ethyl, methyl, ether. So that's the common name. Now, the IUPAC system is a little more rigorous, and I think that's why it's more commonly used now. It can deal with isomers. So if we look at these two molecules, they're actually isomers of one another. If we look at the formula, C1, 2, 3, 4, so that's C4, H, let's count them, 3, 6, 7, 10, O. So C4H10O. How about this one? C1, 2, 3, 4. So C4H, 5, 10, O. So those are both have the same chemical formula, so they're isomers. Now what the IUPAC system allows you to do is name these alkoxy branches when they're on different carbons. So let's look at this one first. The alkoxy branch, the longest chain is those three, so this becomes our methoxy branch. So we're going to call that methoxy propane, but where is the methoxy branch? It's attached to carbon 1, so that becomes 1 methoxy propane. And this other isomer, here's our methoxy branch, but it's on carbon 2. If we number those, there's carbon 2. So the IUPAC system allows us to deal with that because this just becomes 2 methoxy propane. And so the system deals with isomerism. The common name system does not. Here's our branch. There's our, here's our now the common way of naming things will not be able to deal with this isomerism. Here's our 2-methoxypropane, and that would not well, if we were to name that by identifying branches, we still have this propyl and we have this methyl. That would be called, we alphabetize it, and so that would be methyl propyl ether. But methyl propyl ether doesn't tell you that the ether functional group actually comes from carbon 2 of the propyl. So this system doesn't allow for isomers and doesn't allow you to name isomers. So it doesn't work so well for the larger, as soon as you get into larger molecules. So here's a common name. We should be able to draw that without too much problem. Dipropyl ether, so 2 propyl groups, and it's an ether. So there's my ether functional group, and then I just keep adding carbons to make them propyls. So there's my 2 propyls saturated with hydrogens, and there we go, dipropyl ether. Not a problem to draw that. How about the IUPAC name for this? Well, here's a longest carbon chain, happens to be propane, and here's my alkoxy branch, which happens to be a propoxy branch. So the name would be 1-propoxy propane. And again, the common, or the IUPAC name designates where that propoxy branch is on the propane. It's on carbon 1. And if we moved it, we could have a 2-propoxy propane. So the IUPAC system works a little bit better, a little bit more informative. 2-ethoxybutane, well again, we now know exactly what we have to draw. There's my butane. On carbon 2 is my ethoxy branch. And so there is an ethoxy branch on carbon 2. And I would saturate with hydrogens. And so there is 2-ethoxybutane. How about this one? So here we have a benzene with a methoxy branch. So there's my methoxy branch on a benzene ring. So that's just going to be methoxy benzene. Okay, so that's again the IUPAC way to name things. You don't need a 1 because there's only a single branch on the benzene. There is going to be other possible names though, so let's just have a look at some of these. Phenoxymethane. So this is where you take this as a branch. So phenoxymethane looks at this as a branch. That's a phenoxy branch on a methane. How about this one? What's this one? So this is methyl phenyl ether. So again, what we have here is this common name, and so here's my methyl, here's my phenyl, and it's an ether because of that oxygen. So methyl phenyl ether also works. And finally, what about anisole? Well, anisole is the common name for methoxybenzene, so you don't have to know that one. But it does just show you there's several different ways to name ethers. Like in many different organic names, there's often a couple of ways. So let's look at ethers and polarity. An ether group is going to be a polar group. A C double bond O is polar, delta N of about 1.0, so that gives rise to polarity in the molecule. And so with the bond dipole present, you're going to have a molecular dipole, polar molecule. But the positioning of this dipole within a chain means that the proximity to other molecules is somewhat limited. And so you're not going to have the sort of high boiling point because of a polar group. And just to compare here, so here's our propane nonpolar molecule. I'll just draw one thing to your attention. All the molecular masses are about the same. So relative molecular mass between 42 and 46 for these 3 different molecules. That removes one reason why boiling points would be different. So now we're just looking at functional group here. So again, propane with no polar groups, very low boiling point, minus 42. Ethanol we talked about last time. Polar molecule, that's a very strong molecular bond dipole, so strong molecular dipole, so ethanol has a high boiling point, 78 degrees Celsius. We'll look at methoxymethane. Same molecular mass as oxygen, or as ethanol, so there's nothing different there. What we're looking at then is this polarity, this functional group, but it's not as polar, and its proximity to a neighboring molecule will be limited because of the shape of the molecule. This would be delta positive over here, and these hydrogens and carbons are kind of going to get in the way a bit, so the access to the polar component is somewhat limited. So not surprising then methoxymethane has a lower boiling point. It is higher than propanes, makes sense, because it is polar, but it's not a whole lot higher, and it's certainly far less of a boiling point than ethanol. So that summarizes the ethers, the functional group characterized by R single bond O single bond R, or an oxygen singly bonded within a carbon chain. And that concludes this video.